Mr. Bowers doing physics problems. So, here we go. Here we go. This evening I am going to be taking on worksheet 4.1b, which was assigned as homework the other day, and there were a lot of questions, so we are going to take that on currently. Let me go ahead and copy this link over. Link, paste, post, post. All right, so here we are. I am going to go ahead and begin with number 2. I really don't care for number 1. There are too many unanswered questions in number 1, like, is the surface horizontal or is it not? There are a lot of things going on there, so we're not going to really worry about it so much. Long story short, we're going to start with number 2. So, looking at number 2, we have a fellow pulling a sleigh. You got some kiddos in the sled. That's great. And you got this dude out here tugging it along. Okay. We are asked to make a force diagram for the sled and kids. So that defines our system for us. The system we are looking at is the children and the sleigh together as a single system. We are not told anything about the velocity or the acceleration of this sled. So for the purposes of this problem, all we are going to assume is that the velocity is positive, by which I mean in that direction. We're going to make this assumption, and we're going to move forward with it. We don't know anything about the acceleration, so we're going to do the entire problem just not knowing what that is. Okay, so here it is, making our system schema. We have the entire Earth interacting. We have the ground interacting, and we have this rope interacting. The ground is a surface. That makes it eligible to apply up to 2 forces. I'm going to erase my man so that I have enough room to actually do this. There we are. There is our sleigh. We're going to insert the x-axis parallel to the surface, which is the ground. We're going to put in our vertical axis perpendicular to that, and we're going to start through our forces. We have the Earth interacting through a force called gravity. It is down. Done. Gravity is straight down. The surface always exerts a thing called the normal force, which acts to balance out the force of gravity. We have the normal force. We're not going to make any determinations about equalities yet. We're going to wait until we have the whole thing put together and then look at how that works. We can also assume, because this is a practical situation, you can't pull a sled and expect there not to be any resistance from the snow. There is some kind of drag going on here. It's not really called drag, we call it friction in this case, because it is the surface rubbing on the runners of the sled. This is a resistive force. The friction is parallel to the surface and in opposition to the motion. The motion is to the right, so the friction is to the left. The ground is now done. It is executing both of its forces. The only thing left is the rope. The rope exerts a tension, and that tension has to be parallel, or not parallel, the tension has to go along the rope. The rope is going off at an angle like this, so the tension is also going off at an angle. Force, tension. We now have all of the things from our system schema taken care of, so we are out of forces. I'm going to clear myself up a little bit more room here. Get rid of our system schema so we have some room to work. We are going to remind ourselves of the things we know. We know that the velocity is positive. The acceleration we don't know. We're going to write out our net force equations, F net in the x direction. As I look at this, I know that we have friction going backwards, so I'm going to go ahead and insert that. Here's our friction. It is going to the left. This tension is actually pointing in both directions. So I'm going to switch colors here so we can see this a little bit better. The tension is partly pulling up, partly pulling to the right. The way we deal with this is we create a right triangle, just like this. Horizontally, we follow the axis until we get out to the end of the vector. Then we go straight up to the end. Here we now have two perpendicular vectors called component vectors. We label them tension x. This vector represents, this one right here, represents the strength of the pull of the tension, which is horizontal. Again, the tension is pulling in two directions at the same time. It's pulling to the right and it's pulling up. The length of this component vector tells us how much of that force is in the x direction. The vertical part tells us how much of this force is in the vertical direction, and we label this Ty. Now we're able to fill this thing in. We have this force broken into components. The Tx is to the right. The strength of the pull of tension, which is directed toward the right. Hello, whoever has just joined the channel. Please say hello, that way we know who is here. And if you have any questions, please feel free to type them into the comment section, or not the comment section, the chat window, so that I can respond. Okay, we don't know what this is equal to. We don't know because we do not know what the acceleration is. We have a couple of options. If this tension force is larger than this frictional force, we will have a net force to the right, which will cause an acceleration to the right, so the thing will be speeding up. If the friction is larger than the tension, then we'll have a net force to the left, which will cause an acceleration to the left, which would mean the sled would be slowing down to a stop. We don't know what the sled is doing, so we can't make any further determination than that. In the y direction, we have three forces. We have the normal force, up. We also have this component of the tension. The tension is a little bit pulling up. So we indicate that here, minus the force of gravity, which is pulling down. In this case, we do know that this has to be equal to 0. We know this because we understand this motion vertically. The sled is not flying up into the air. The sled is not burrowing into the ground. It is not moving vertically at all. There's no acceleration vertically. That tells us that there is no net force vertically. These things have to add up to go to 0. Moving forward to number 3. Number 3 has us looking at a person leaning up against a table. So we have this table, we've got a person. The person is standing on one leg, so they're trying to balance themselves by leaning up against this table. We are to draw a force diagram of the table. Going into our system schema, this is number 3. We have an interaction here from the person. We have an interaction here from the ground, and we have another interaction from the entire Earth. These take care of all of our shield forces. They also take care of all of our contact forces. We go to make our force diagram. Our surface, in this case, is horizontal. We're looking at the ground as the surface. So our vertical axis is vertical. There's X and Y. The Earth pulls straight down, as always, with gravity. The Earth is now done on our system schema. Goodbye, whomever was watching. we have to deal with the ground. The ground, being the surface, is capable of two forces. One of those forces is straight up. It is the normal force. Surfaces always exert a force at 90 degrees to themselves. It's called the normal force. It is straight up. We're again going to reserve judgment about the relative size of these forces until we have all of the forces on the table. The ground is also exerting a frictional force in this case. We have to figure out which way. Okay, so we're actually going to hold off on the friction. Let's just put that one on the shelf and figure out what this person is doing so that we can decide which way the friction has to go. All right, the person is pushing down and to the left on the table, right along their arm. So when we insert this force, we are going to insert it down and to the left, and we are going to call it force push. This is the person pushing on the table to hold themselves up. Hello, viewers. Please say hello so we know who we're talking to. So we have this push. The person is now taken care of. Again, looking at the picture, thinking about this in our minds, you're putting your hand on the table, you're pushing down and left. So we indicate that by making the force in that direction. This tells us which way the friction has to go. We know that this table is not moving. Because it is not moving, we know that there has to be some force in this direction to cancel out the fact that this force is to the left. We need a force to the right to cancel out a force to the left. So we're going to put that in. We have to have a force here to cancel this force out. What is causing it? Well, it's not the person. We've already accounted for that. It's not the Earth. We've already accounted for that. The only thing left is that this is a force by the surface. We've already put in the normal force, so the only thing left is this frictional force. That is the only force left to us, so it must be it. Now we're prepared to go look at our net force equations. All of the forces are accounted for because all of the interactions are accounted for. Making some space. Need to get a bigger whiteboard. We're going to look at the net force in the x direction. We're going to look at the net force in the y direction. Examining this thing horizontally, we know that this person is static. The table is static. That is not moving. It's not moving, it's not going to move, so we know that the acceleration is 0 in both directions. It's not sliding horizontally, so the acceleration horizontally is 0. It is not moving up and down, so the acceleration vertically is also 0. We have this weird push force. It is not behaving itself. It's not simply acting in one direction or the other. It is acting in both. So we take this vector, we break it into components so that we can get a handle on how much is it pushing in each direction. We go out to the end of the vector. We create a right triangle where one of the legs is along the axis. It's pointing to the left. The other leg is parallel to the other axis, pointing down. We can name these forces. This is the force of the push in the x direction. This is the force of the push in the y direction. And again, we have a right triangle here. This vector represents the strength of the push to the left. This vector represents the strength of the push down. These two together are this single push down and left. We're now able to fill in our equations. Looking in the x direction, we have two forces. We have the frictional force to the right minus the push, which is to the left. We know that has to go to 0 because our acceleration in the x direction is 0. Vertically, we have three forces. We have the normal force up, minus the push in the y direction down, so it's negative, minus the force of gravity. We know that this has to be equal to 0 because it is not accelerating vertically. If these three forces don't add to 0, then we would have an acceleration in that direction. We don't have such an acceleration. Moving on to number 4. We have a man. He's hanging off these ropes. The man is the system. Identifying all of the interactions. We have from over here, the rope acting from the right. From over here, we have the rope acting from the left. And we have the entire Earth interacting down here. These are all of the interactions. There is no surface. There's nothing else touching the guy. These are all of our interactions. So we go to make our force diagram. We're going to allow our x-axis to stay horizontal. There's not really a reason to change that. The gravity pulls straight down along our y-axis. F, gravity. The tensions being in the ropes, the force of these ropes, are exactly in the direction of the ropes. So the rope to the right is pulling up and right, and the rope to the left is pulling up and left. Because this is actually a single rope, we know that the tension here and the tension here have to be the same thing. The tension in a rope is the same at all points in that rope. So here are our forces. We have now two vectors which are not behaving. They are not pointing along our cardinal directions, so we're going to break them into components. We go out to the end of the vector, draw a right triangle, this one pointing to the right along the x-axis, this one pointing up parallel to the y-axis. This forms a right triangle where the original vector is the hypotenuse. We call this tension in the y. We call this tension in the x. They represent the strength of this tension in each of these two directions. We do the same thing on the other side. We draw a right triangle. We draw a right triangle to the left and up because the original vector is to the left and up. Tension in the x, tension in the y. Making some space. We know that our man is static. He is not moving. His acceleration to the left and the right is 0. This implies that the force in the x direction is 0. We know that he is not accelerating up and down. He's not moving at all. This implies that the net force in the y direction is also equal to 0. If we have an unbalanced force, then we must be accelerating in the direction of the unbalanced force. Writing out our equations, F net in the x direction, we have two of them. We have the tension to the right minus the tension to the left. We know that these have to be the same thing because we know we cannot have any acceleration. We don't have acceleration to the left or right, so the forces have to balance out. The same thing vertically. F net vertically in the y direction, we know that this thing has to go to 0 because we have no acceleration vertically. We have the tension up plus the tension up minus the gravity which is down. These three things have to balance out and go to 0. Moving on to number 5. We have a squirrel sitting on a roof. He's like sitting here eating something. That's what squirrels do. Fluffy tail. Fluffy tails are important if you're a squirrel. Things we know about this squirrel to start. The squirrel is static. That means the squirrel is not in motion. This tells us that the acceleration of the squirrel is 0 in all directions. Horizontally, he is not moving. Vertically, he is not moving. The squirrel is not moving. He is not going to move. The squirrel is our system, looking at things that are crossing the line. We have the entire Earth interacting with the squirrel. We also have the roof interacting with the squirrel. This is our surface. Surfaces are capable of exerting 2 forces, the normal force and frictional force. So we go to make our force diagram. In this case, we have a slanted surface. So when we go to make our force diagram, we are going to put in our x-axis, but we're going to put it in parallel to the surface. Here's the roof. There's our x-axis, parallel to each other. This is a very important step. It will simplify your life. It seems complicated, but it actually makes things way, way, way easier. The y-axis has to be perpendicular to the x-axis, so it is straight up and down from the x-axis, 90 degrees in there. X and y-axis must be perpendicular to each other. The x-axis should be parallel to the surface. Now we can put in our forces. This guy, the entire Earth interacts with gravity. Gravity pulls straight down towards the center of the Earth. It doesn't matter what's going on with your axes. The gravity pulls straight down anyway. A surface always exerts a normal force. The normal force is always perpendicular to the surface. The surface here is slanted, so our normal force has to be normal to that, perpendicular. There's our 90-degree angle. If we were to stop here, because the question becomes, is there friction or is there not friction? If we were to simply stop here and look, we'd say, okay, well, relative to the roof, the normal force is pushing straight up. Relative to the roof, gravity is pulling down. There's a chance that those two things cancel each other out, and that's okay. So the squirrel is not going to fall through the roof. The squirrel is not going to launch up into the air. We have balance this way. But when we look horizontally relative to the roof, the gravity is actually pulling the squirrel down the roof. There is a component of gravity which is pulling the squirrel along the roof. Here's our Fg in the x direction. There is no force to stop the squirrel from sliding down the roof. So we know we can't be done. We know that the squirrel is not sliding off the roof. So we know that we need another force to hold him up. And fortunately, the roof can provide that force. We've only done one of these two forces, so we can have this additional force of friction, which serves to counteract this component of gravity down the roof. So we have the normal force up counteracted by the force of gravity in the y direction, which is down. We have the force of gravity in the x direction, down the roof. We have the frictional force up the roof. We know that these things aren't that the squirrel is not accelerating. So when we go to our net force equations, we have two forces in the x direction. The friction minus Fgx, the strength of the gravity which is pulling along the roof, that's got to be equal to 0. We have F net y. In the y direction, we have the normal force up. We have Fgy down. Those have to go to 0. we know that the squirrel is not accelerating in any direction, not along the roof and not up off of the roof. So in both of those directions, the net force has to cancel out. Skier. We have a skier going down a hill. Here's the slope. We got our skier. He's on his skis going down the hill. We are told in this case negligible friction. The word negligible simply means it is small enough that you can ignore it. It's there, but it doesn't matter. This tells us that our surface, in this case, the ground, exerts no friction. Here's our system. Here are our interactions. We have the ground, which is the surface. But again, we're told that there's no friction. And we have the entire Earth pulling him down. We go to our force diagram. We put in our x-axis parallel to the surface. Here's our surface. We make our x-axis parallel to that, our y-axis normal to our x-axis. Gravity pulls straight down. The Earth pulls things with gravity directly towards its center. It cares nothing for how we've defined our x and y axis. Straight down. The ground, in this case, is only exerting a normal force. The normal force is always perpendicular to the surface. Here's the surface. There's perpendicular to the surface. We know it has to be up so that it can counteract this force of gravity. Gravity is not behaving. It isn't along one of our axes, so we break it into components. We draw one component along one of our axes, right out to the end. There's our right triangle. There's FG along the y-axis. Here's FG parallel to the x-axis. We form a right triangle where the original vector is the hypotenuse. We now use these two vectors instead of that one. Gravity is pulling down the hill and into the hill, so we replace it with one vector pulling into the hill and another vector pulling down the hill. We can now go to our net force equations. We're all out of things. The surface is done. That's done. No more interactions, no more forces. Writing our net force equations. F net in the x, we have one force. F net in the y, this way we have the normal force minus the force of gravity acting in the y direction. Can we say these are equal to anything? Well, we have one force, it's not zero. We don't have two things. If we had two things, we could say, look, these two things, they add together, they go to zero, they cancel out. But we don't have anything pulling up the hill. There's nothing to stop gravity from pulling this skier down the hill. So it's not just that he's going to move down, he is actually going to accelerate down the hill. In the x direction, we have some acceleration. In the y direction, this way, well, let's look at the skier. Is the skier accelerating up or accelerating down relative to the hill in this plane? No, he's not. There's no acceleration in this axis. So we know that there cannot be any force left over in that direction. Gravity is pulling the person into the hill. The hill is pushing just hard enough to keep them from going into it. We're not going to do anything with that yet, but soon. There's the skier. Kid on a swing, number 7. I'm not not even gonna draw those things. They're just gonna get in the way. We got a kid on a swing. Here's the string. There's the seat. There's a guy. Pulling up on the swing. Little kid sitting in the swing having super amounts of fun. Just like us. Super amounts of fun. The system is the child. The system is the child. So here's the child. We have to isolate all of the interactions. What is crossing the line? The rope is crossing the line. The seat is crossing the line. This person is crossing the line. And the entire earth is crossing the line. In this case, we do have a surface. It is this seat. That seat right there is our surface. So it is capable of two forces. Whether it's actually exerting them both or not, we don't know, but it is capable of two. We make our force diagram. We put in our x-axis parallel to the surface. Our seat is angled, so we're going to put our axis in with a dotted line. There's our x-axis, parallel to the surface. Vertically, there's our y direction. Gravity pulls straight down every time. The normal force is straight up from the surface every time there is a surface. Here's the surface. The normal force is straight up from it. We have this person pulling backward. For simplicity's sake, we're going to simply say, look, that person is pulling straight back on the seat. This is a pull. We did that. We did that. Oh, we need another force. We have not accounted for this rope. Ropes are only capable of pulling, and they are only capable of pulling along the direction. So this rope is also pulling straight up along the rope. These two things are parallel to each other, and this is our force of tension. Well, this isn't actually that bad. These two forces are parallel with the y-axis. This force is parallel with the x-axis. We only have one misbehaving force. That's gravity. So we break it into components. We follow one of the axes down to the end of the vector such that we form a right angle. There's our right triangle. This vector represents the strength of the gravitational force along the y-axis. This one represents the strength of the gravitational force in the x direction. This kid is being pulled back. They're being pulled back. We're going to assume, for simplicity's sake, that the kid is being pulled back at a constant velocity. So our velocity in this case is in that direction, parallel to the surface, and it's constant. Because it's constant, we know that the acceleration in that direction is 0. We also know that the kid is not accelerating in this direction. The kid is not falling through the seat. The kid is not lifting up off of the seat. So we know that the acceleration in the y direction has to also be 0. This tells us that our net forces in both directions have to cancel out. Let's make sure that works. Make some space up here. F net in the x direction. We have the pull that way minus Here's our force of gravity along that direction, force of gravity in the x direction. Those two things have to go to 0 so that this kid is being pulled back at a constant velocity. Net force in the y direction, we have two upward forces. We have a tension plus the normal force minus the force of gravity in the y direction. This has to be 0. If it weren't 0, if the tension and the normal force were larger than the strength of gravity in that direction, then the kid would be accelerating up out of their seat. If the force of gravity were larger than the tension and the normal force, then the kid would be accelerating down through their seat. Neither of those things are happening, so we know that this whole thing has to balance out. Person climbing a hill. We have a hill. There it is. Off of the hill, there's a tree growing. There's a person climbing the hill with a rope that is parallel. Looking at the picture, that rope is pretty much parallel to the surface. This person is stopped, so they are at rest. It says in the statement of the problem that the velocity is 0 and that there is no change in velocity. The person is static, not moving, not going to move. So we know that the acceleration is also 0. This is in two directions. The person is not accelerating up the hill. They're not accelerating down the hill. That means that their acceleration in that direction, which we're going to call x, up and down the hill, has to be 0. The person is not accelerating through the hill. They're not accelerating up off of the hill. This is our y direction. They're not accelerating that way, so we know that the acceleration in the y direction is also 0. Completing our system schema, we have the ground, which is our surface. We have this rope, which is providing a tension, and we have the entire Earth providing gravity. These are all of our things. We might have 4 forces. The ground will always exert the normal force because it's the surface. It might exert the frictional force. We put in our x-axis parallel to the surface. Here's our surface. There's our x-axis. The y-axis goes in normal to the x-axis. Gravity pulls straight down. Earth is done. The ground exerts a normal force straight up off of the surface. The rope can only pull along the direction in which the rope is. The rope is parallel to the ground, which is our surface, so the tension is going to be along the x-axis. Here's our tension. So the question becomes, is there friction? Let's leave off friction for a moment, and we'll swing back and see if we end up needing it. Net force in the x direction, we know this has to be 0. Let's look at what forces we have. Well, gravity is once again misbehaving. It's not along one of the axes. So we have to break it into components. There's the portion of it pointing in the x direction. There is the portion pointing in the y direction. This forms a right triangle with the original vector as the hypotenuse. This is the force of gravity in the x direction. This is the force of gravity in the y direction. In the x direction, we now have 2 forces. We have tension up the hill minus Fgx down the hill. Is it possible that these 2 forces are exactly identical and this thing is equal to 0? Yes. Yes, it is. Is it also possible that the gravity is bigger than the tension? Yes, it is possible. If that's the case, the person would be sliding down the hill. They'd be accelerating down the hill unless there were another force. If the tension is smaller than the gravity, then the friction will act up the hill. That wasn't a very good job. The friction will act up the hill to help the tension hold the person up. Think about climbing a hill. You can set your feet in the ground to prevent yourself from sliding down. So you're holding the rope, your feet are also in. The harder you dig in with your feet, the less hard you have to pull on the rope to keep yourself up. Or you could actually kind of push. You could lean back, set your feet the other way, and actually kind of push up the hill and really lean into the rope, in which case the friction would be the other direction, and the tension would have to be big enough to compensate for both of these things. So at the end of the day with this problem, we don't know which way the friction is going because we don't have enough information. We could create a situation where, look, the friction doesn't even exist. These two are exactly equal. We don't need friction. If this is bigger than the tension, then we need friction up the hill. If the tension is bigger than the force of gravity in the x direction, then we need friction down the hill to compensate for how big the tension is. It's all dependent upon the situation. Probably easiest just not to worry about it in this case. Net force in the y direction. We know that this is also equal to 0. We have the normal force up off of the hill minus FGY down into the hill. This is gravity pushing the thing into the hill. This is the hill pushing the thing up off. That's equal to 0. There are no other possible forces in that direction. Looking at the book on the lectern. I'm going to look at this problem in the simplest way possible. Here's our book. The book is the system. Here are our interactions. We have this surface. We have this surface. We also have the Earth. We have two surfaces. Which one are we going to call X? Well, I'm just going to arbitrarily choose this one. Why? Because it makes me comfortable. Luckily, these two surfaces are both, they're 90 degrees to each other, so our life actually works out pretty well. I'm going to call that one X, parallel to this surface. This one, which is parallel to the other surface, we'll call Y. They are conveniently parallel to each other. That's really essential. We have to have our X and Y axis parallel to each other. Gravity always pulls straight down. This surface here is exerting a normal force perpendicular to itself. Well, here's parallel to that surface, so the normal force has to be up and this way. This part of the lectern is holding the book up. We'll call that the normal force number 1. So we'll call that surface 1. This will be surface 2. Surface 2 is providing a normal force, normal to itself. Here's surface 2. It's providing a normal force this way. That this surface is holding the book up in that direction. F normal 2. Do we need gravity? Or do we need friction? No, we don't need friction in this case. Is it there? Maybe, maybe not. We don't know. If we completely ignore it, that's fine. It's not going to make any difference to the problem. That book is not moving. It is static. The acceleration in the x direction is 0. The acceleration in the y direction is 0. There is no motion. There is not going to be any motion. That's it. Our gravity is once again misbehaving, so we're going to break it into components. We draw one component along one axis, right out to the end so that we form one leg of a right triangle. We then draw in the other leg of the right triangle such that the gravity is the hypotenuse. This is the force of gravity along the x-axis. This is the force of gravity along the y-axis. They represent how hard is gravity pulling into the bottom of this thing. This one represents how hard is gravity pulling into surface 2. We know that our net force in both directions has to be equal to 0 because we are not accelerating in either direction. So the net force in our x direction has to be 0. We have two forces in that direction. We have the normal force, 1, minus the force of gravity in the x direction, that's 0. We have our net force in the y direction. We know that has to be 0. The book is not accelerating this way. We have two forces. We have the normal force 2 pushing up that way. We have the force of gravity in the y direction pulling down the other way. These have to be 0 because there is no acceleration. A net force results in an acceleration in the direction of the net force. We know there is no acceleration because of the setup of the problem. That lets us say that there is no net force in this problem. And last one. Turns out that it just takes 50 minutes to do this. Alright, we are going to draw a force diagram for the person when they are stepping. And then we are going to draw a force diagram when that stepping foot strikes the ground. Okay. So we have this person. They've got one foot there on the ground. They have another foot that it's up off the ground. They haven't struck the ground yet. Okay, so to analyze this motion, we're going to look at the person, but we're really going to focus what's going on with that foot. Okay, so we're going to look at the whole person, but we're really going to talk about what's going on with this back foot right now, in this first case where we're interested in when they're stepping. Here's our person. Stuff that's interacting. We have the earth. We have the ground as our surface. Drawing our first force diagram. The surface is parallel. Well, we draw our x-axis parallel to the surface. The surface is the ground. It's horizontal. Our y-axis is then straight up and down. Gravity pulls straight down. The normal force pushes straight up. The question is, what is the ground doing to this foot? Okay. And if we think about when we walk, you can even get up and actually take a step. Feel what your back foot is doing. You're pushing back and into the ground. The person is exerting a force into the ground. That way. The ground responds by pushing back. The ground is capable of two forces. We already have one of them, the normal force. In response to the fact that the person is pushing back on the ground is going to push the foot forward. Our frictional force here is actually in the direction of motion when you take a step, and so we call that a traction. This is a frictional force caused by the surface. It's parallel to the surface, but it is in the direction of motion, so we don't call it friction, we call it traction. Looking at our net forces, we're all out of things to interact now, so we have to be done. There are no more interactions to put on our force diagram. F net in the x direction, we have but one force, the traction. This means that when you step forward, you are accelerating in the direction of that step. In the y direction, we are not accelerating up off the ground, we're not accelerating into the ground. The acceleration is 0, so the net force is 0. There are two forces, the normal force up minus the gravitational force down. They cancel each other out. So there's part A. Looking at part B. Now we're looking at when that front foot hits the ground. Now our front foot has actually hit the ground. So we're not pushing anymore back here. This foot has simply hit the ground, and you can feel when that foot hits, especially I'm wearing socks on carpet right now, I can actually feel my socks being pulled back on my foot. Okay, here's our person, our interactions. The earth and the ground. The ground is our surface. We put on our x-axis horizontally because the ground is horizontal. Gravity pulls straight down. The normal force, 90 degrees to the surface. But in this case, when this foot hits the ground out in front of us, it's trying to slide forward. You're not pulling with that front foot, it's hitting the ground. This actually slows you down. The friction is pulling back on that. Again, if you're wearing socks and you step, you can feel the sock being pulled up your foot. We have a frictional force backwards. So when we go to look at our net forces in the x direction, we have this frictional force, which is backwards in the negative direction. This tells us that we're actually going to accelerate backwards. So when you step, your forward step accelerates you in one way. When your other foot hits the ground, it actually causes you to accelerate the other way. So while you walk, your acceleration oscillates with every step. Positive, negative, positive, negative, positive, negative, because of what's happening with these forces. The back foot we're pushing off, that's giving us traction forward. When the front foot hits the ground, it stops us from moving forward. In the y direction, we know that that has to be 0. This person is not accelerating up, they're not accelerating down. The normal force has to be balanced out by the gravity. Fiend, thank you for signing in and checking things out. The video will post briefly. I think that Google has to do some encoding or something before the video becomes available to watch afterwards. So thank you for tuning in and have a great night.